Thank you, Professor Miraela, for the kind introduction, and thank you also for the organizer who gave me opportunity to share our work with you today. I am Jacques Noudem from Caen University and from Christmas Laboratory in France. I'm going to talk about spark plasma sintering, basically about identification of functional materials. First of all, let me thank all the co-workers from this work, from different labs in France, and also our colleague from SIT in Tokyo. Where is Caen? Caen is located somewhere here between, let's just say, Paris and London, close to the English Channel, like you can really observe here. In our state, you can visit such kind of nice monument named Mont Saint-Michel. Well, like I point out, I am from University of Caen, where the president is Professor Pierre Denis. It's one of the older universities in France, founded in 1432. And after the Second World War, this university was destroyed and reconstructed in 1957. Roughly, in the university, you have around 30,000 students and 3,000 staff. And the building in our campus was also classified in 2012 as a historic monument by French Ministry of Culture and Communication. Well, my today's talk will be, I'll try to answer two questions. What is the power plasma sintering, where I give some principle and mechanism? And the second question will be, what can we do with such kind of devices? Well, I will just try to answer and show some example about the two materials, the magnesium diboride cryomagnet superconducting materials and the permanent magnet neodymium iron bar before to give some conclusions. What is the spark plasma sintering? This is the non-conventional sintering technique where we are going to combine the very high current and high pressure, mechanical pressure, to prepare the materials. It's the faster heating technique rate, sorry, this gives a faster heating rate, 500 up to 500 and sometimes 1000 degrees C per minute. The lower temperature, you can, if when you have some materials, you can center 200 degrees C below the temperature where we use when you use the conventional sintering or hot pressing technique. It also gives some shorter processing time, less than an hour. And basically, the main aim of this technique is the kinetic of the sintering is quite higher. One of some benefits of this spark plasma sintering named SPS technology are the significant sample densification, the grain growth control, and also you can also induce some grain alignment. But the main condition here is to have the lamellar structure materials or some let's just say layer shaped compound, where by applying the pressure at high temperature, you should be able to control the grain alignment between grains. Compared to the traditional technique, this technique, SPS, requires an hour to reach the peak temperature, like I already pointed out. Basically, the SPS, for the SPS technology compared to the conventional one, where you need, compared to the SPS, where we need only a few minutes, if you compare to the traditional way to prepare the materials. The clear benefits of this technique is that this technology gives some significant saving time and energy, and some capacity to retain the nanostructure, which can be correlated to the properties of the materials when you are going to prepare. The other advantages, let's just point out, the preform and bender are not necessary in this technique. You can prepare some near net shape, that is quite possible, and also welding without filler materials. But as the main technique, some advantages, some disadvantages exist, like the cracks apparition for some brittle ceramic materials. The low oxygen content when you're going to prepare the oxide materials, because like I will show you, we use the vacuum chamber for the oxide. This will be not quite suitable for the oxygen contents, and also some thermal gradient. But one of the open question is, can you really prepare some batch process easily by use such kind of techniques? Let's just try to give you an answer in a few slides. The SPS, just to summarize here, versus a large family of materials. By using this technique, you can prepare some ceramics, polymers, some metals, and composite materials. Like a various kind of compounds can be possible by using SPS technique. Well, how this work like? Just to give a few words about the principle. It's like the hot pressing technique. Because you have just the heater compared to the hot pressing or the conventional one. The heater is not the resistive element, but here you are going to use the power supply. You can clearly observe here to heat the samples. And the upper part is the hydraulic system to apply the pressure. And the mold and sample is located inside this chamber. This is the vacuum chamber, where you can also use some inert gas, argon, nitrogen, or the mixture of argon and hydrogen for some metallic system. Well, to prepare the samples, you are going to combine the powder where you'll put inside the dia, here graphite dia, basically, and you're going to use also some graphite piston here, but put the graphite foil around before to put the powder inside. But now when you want to heat some materials above 1500 degrees C, you should also put some graphite around to save the temperature and also for homogeneous temperature. Basically, here you have the mold inside the chamber. This is the both electrode where you also have some cooling water, and during the heating you can clearly observe here. But the main parameter here is to take care about the electrical and thermal conductivity of materials and dia. The idea here is to avoid the thermal expansion coefficient. Basically, here you have the typical thermal cycle where you can apply. And the red color is the thermal profile. The green one is the pressure applied, but the important curve here is the black one. This is the shrinkage curve for the densification, where you can clearly observe here after 4 minutes, you attain the plateau. That means the samples, the submicron alumina oxide is full dense. But the green one, the blue one here is the derivative curve. The speed of the black one show that the maximum here is in the middle of this inflection point of this black curve. This is basically the sintering temperature of the materials when you want to optimize all this. Basically, let's just say when you put the powder inside the mold and during the heating, according to the FCT, you can clearly observe here, you start to heat, let's just say between the grain boundary here by Joule effects before to heat all our powder samples. And how this, the sintering mechanism, SPS versus what I call here conventional sintering, you can clearly observe here in the initial stage, you have some neck formation. And then the expansion of this neck in the next step, and then the plastic deformation. And at the end, you can clearly observe like the neck formation of the form between two grain boundary in the case of SPS. If you can compare with the conventional sintering one, where you have again this neck formation in the both cases. This again confirm like the Joule, confirm this Joule effect between the grain contacts. Well, concerning the SPS, let's just say there are three main provider of this machine: the Syntex in Japan, the FCT in Germany, and Thermal Technology in UK. Since less than 2 years, you have Suga also in Japan, who propose some devices. And here you have the three main devices proposed by these three companies. Syntex one, this is the equivalent devices. FCT is the one where we use in our lab, and Thermal Technology. We use this one in our lab where we can apply the force of 25 Newton. The dia, you can prepare the sample up to from 8 millimeter to 80 millimeter, and the maximum temperature attained is 400 degrees C. And here you have again the new company in Shanghai who proposed some mini SPS were designed for the DEX devices, where you can clearly observe here. Here you can just apply 3 tons forces, then the maximum current where you carry is 2000 amps. Well, using SPS, can you prepare the many samples at the same time? The answer is the FCT proposed this design to say you can design the mold in parallel, like you can clearly observe here, to prepare many samples at the same time, or in series, like you can clearly observe here, or combine series and parallel to prepare many samples. And when they do that, they make some tests. They was able to, by design these multiple tools, the multiple process pressing tools, they was able to produce many samples like you can clearly observe here in this slide. And then they show that if they can combine, after design the new mold, combine series in parallel, they was able to prepare 46 pellets at the same time, like you can clearly observe here. The sample is located between all these two tools. Well, but when you do all this, you should take care about something, about the thermal gradient, like I already pointed out. Temperature gradient is more important. This is the standard tools design, where you can clearly observe here you have the huge thermal gradient. And then they was able to optimize the tools, where you can clearly observe here, you should be able by finite element modeling to optimize this thermal gradient. And this was why they succeeded to produce the batch of samples, many samples at the same time. But another question is, can you produce the large size of samples, large diameter? But the answer is, this is quite difficult, because the FCT again show that in this diagram, like when you want to prepare the large piece of samples, you can clearly observe again, you should avoid this thermal gradient. And to avoid this, they propose what they call here the SPS arc heating technology. That means they add here inside the machine some additional heat induction resistant heating system, like I'm clearly observe here. And they was able to produce such kind of large samples without any thermal gradient. And this was confirmed when you clearly observe here the shrinkage curve. This is the standard one, blue one, and the hybrid system, where they was able to shift this. This is why they succeed to produce this large sample without by minimize the thermal gradient. Well, let's just now come to the second part of my talk and to answer the second question. What can we do with the spark plasma sintering? Well, let me start with the identification of magnesium diboride superconducting by SPS. Well, like I didn't know what will be the audience, I just put one slide to again point out what is the superconductivity. This phenomena is known more than 1 century, where the resistance should be 0 below the critical temperature named TC. This was discovered by Carmelin Honest. Then the second effect of the superconducting is the Messner effect, where when you cool down the superconducting materials below TC, you should be able to levitate, because you have the field, magnetic field will be out, should be able to levitate the magnet above the sample, like you can observe here. Well, the objective of this work for us is to prepare to optimize the bulk MgB2 materials as a compact magnet. But what we are looking for is to use this for some application around 20 to 25K. What is the magnesium diboride? The system is well known since 1953. The stoichiometry seems to be quite simple, hexagonal structure. Then, but the superconducting was discovered in this system in 2001, where the TC is 39K. Some advantages exist as this material is quite strong mechanically, quite less. You have some low-cost materials and also low density, seem to be light materials. But when you now you observe the powder in these two figures, I show the initial powder, but when you compare with the conventional sintering materials as MgB2, the density is quite low. That's 36% only. It's why the main thing is to, by using SPS, to densify this material, to increase the density. The starting powder here is or start company powder or from Pavesium company, the MgB2, or to mix MgB2 magnesium with boron or boron coating. Basically, when you put here, you have our powder inside the bowl. By using SPS, we will apply the pressure and current to densify it and record the shrinkage curve like you observe here. And the sample densifies quite well. Well, this is, let's just say, the various shape where you can produce by using this SPS easily. The density can up to 98%. And regarding the superconducting properties, the TC is around 39K on this material. You have here the temperature dependence of magnetic moment with the TC. But to estimate the critical current density on this material, the hysteresis curve was recorded. This is again the magnetic field dependent of magnetic moment, where you perform in such small cube samples. You see the shrinkage curve, the hysteresis curve at 20K, and from this, it was able by using big model to deduce the JC, and the result are shown in this curve. The magnetic field dependent of JC clearly show that the temperature, the JC, let's just say you have the different JC according to the processing temperature. But the surprise is when you identify the material, the JC decrease. Densify the material, the JC decrease here at the cell field when you increase the temperature. The answer is because when you increase the centering temperature, you improve the magnesium diboride inside the material. And this could be one of the reasons why the JC decrease in that case. Well, when you look the microstructure on this all these samples, this is 850 degrees C. The sample seems to be quite porous. You still have some porosity at 950 degrees C, but the sample is, the grain size increase in the sample is more dense when you increase the temperature. Well, what do you name? I name here this JC versus the critical current density versus starting powder. This powder was prepared by the colleague from Japan, from SIT, magnesium diboride by using nanoborons, or magnesium diboride here where the boron was cut with the carbon. What we can learn from this curve? First, all the three samples was prepared in the same condition, 850 degrees C, 100 megapascal during 20K. What you can observe is at the low magnetic field, again, the JC increase, like you can really observe here in these two cases, when you use the reactive synthesis here compared to the conventional material where we use the commercial powder in that case. But now at high temperature, what happened? You can clearly observe here the coating materials seem to show the high JC compared to the one without coating material. The question was why? But in that case, you can clearly observe again the JC increase here because we improve the density of our material. But the answer from this is here. When you look at the microstructure on the board curve, you have some small grain size in that case compared to that one. That means we improve the pinning in this case compared to that one. This is one of the reasons where the JC really increased. Or if you compare with the magnesium diboride, who was here prepared in the same condition, the microstructure was here. You can see the grain size is quite high. You have a very big grain size and also quite porous materials. Okay, the TEM confirmed this small grain size on these materials where you can clearly observe here this nano grain size, roughly around 100 nanometer grain size. Well, let's just move now to the another characterization concerning the levitation force, where our sample is located here inside the cryostat, cooled by cryocooler. You have some sensor and the magnet here to perform. Where this is the levitation force measurement on different samples. These different samples have a different diameter at 20K. Again, magnetic levitation force here is related to this formula, where you have here the magnetic moment and the magnetic field gradient. This magnetic field gradient is depend to the magnet where you have here on top. It's generated by this magnet. You can clearly observe, again, this magnetic moment is depend now to this Brown formula, where this is related to the JC and also related to the sample size. This is the reason why you can clearly observe here, like the levitation force increase when you increase the sample diameter here, up to 45 Newton in that case. Well, he was able to prepare again in the big sample, 70 millimeter sample, where it was able to generate, to perform, to measure, like can clearly observe here, the high levitation force up to 225 Newton on top of this material. But this was performed again, like can clearly observe, you are quite far from the surface of the sample, because in our system here you have U blue here on top. You cannot go close to our samples. That's why you can observe here the gap is quite huge. That means if you was able to go quite close, you should be able to perform or to measure the very high levitation force on top of these samples. Well, how about the trap field? Because I'm saying this work for us was to prepare the cryomagnet samples. You can clearly observe here in our sample where you put, it was 20 mm samples, where you put two hole sensor between, you was able to trap, like you can clearly observe in that case, roughly 4 Tesla on top of the sample. But you should just take care about how to say the speed of the magnetic field where you apply, because if you cannot control this, you will have observed such kind of flux jump, like you can clearly observe in this dot curve here. But this value obtained can be compared with some reported data, where at 20K, by stacking again the both samples, some colleague was able to trap around 3 Tesla here. When you are here around 20K, you should be able to deduce in the both condition here, roughly again 3 Tesla. That means the reservoir you obtain is quite comparable to some reported data. Okay, let's just come back to the last part of my talk just to share with you some results obtained in the permanent magnet. This is one of our ongoing projects for the national project here in France, in the framework of the national project in France, between these 3 partners, people from Grenoble, from CNRS and Grenoble, and Niel Institute, and also the Valeo company. The main goal of this work is to develop the second life magnet using neodymium iron bar magnet powder obtained from urban mine deposit. I mean, you can use some hard disk, electric engine, etc. And the question is why this recycling magnet? Why to recycling this? Is you have some sustainable growth of rare air demand around the world. This is one of the question. Another is the increase of the urban deposit. You can clearly observe that means in this project we are going to use from Valeo engine to remove some second life, some magnet or some end life magnet, like you can clearly observe here. And then the people from Grenoble should be able chemically to refine all this bulk magnet in powder. And for us in COW, we should be able, our role in this project is to form again, to sinter again this powder to obtain some magnet. We are used to microwave heating or SPS to prepare the materials. Okay, how about the result on this system? We start with 2 powder. First, the commercial powder produced by this Japanese company, Aishi powder. You have here the composition, the chemical composition, and the how the grain size look like, the shape of the grain size. And now the recycling powder named H90, we name H38. Here you have again the grain size and the shape of the samples. This was from value electric motors. Then how about the shrinkage? The SPS gives us here the first answer. Like this, this is the Aishi, the red curve is the commercial powder, and the pink one is our, let's just say the recycling powder. What you can just learn here is the shrinkage is quite, not so far, but this can sinter easily. This show us some excellent sinterability of this powder. And the sample where we obtained was quite dense, around 98.5%. And how about the magnetic properties of this? But let's just, before to give you the result of what you obtained, to show you what we deduce all this. Magnetically, we make the hysteresis cycle. And from hysteresis cycle, you are going to deduce what you call MS. Here is the saturation or the saturate magnetization. And then you are going to use also MR, who is the remnant magnetization here, when the field will be zero, the applied field will be zero. And the last parameter is SC, is the coercive field. And we perform this first on the both powder. Here you have the characteristic and the result where you obtain in this both powder, Aishi, and the recycling powder. And then how about now the sample where we perform by SPS? By SPS, this is the result where you obtain, again, you have the hysteresis curve, the magnetic field dependent of magnetization, the both powder, Aishi powder, and recycling powder, the red color here. This is the result where you obtain is quite close, but the main parameter is the energy where you are going to deduce the magnetic energy in the both curve, where you obtain roughly 50 megagauss Oersted in the commercial powder and roughly 13, that's 15 and 13 in the recycling powder. But the coercive parameter, coercive magnetic field was less than 21% compared to the starting powder, like you can clearly observe here. And then you was able to record the magnetic field mapping in the board curve and compare with the commercial available magnet. This is the commercial available magnet where you obtain 0.3 Tesla. And then we take our we prepare two bulk magnet with the commercial one and with the recycling one. And this is why we was able to obtain roughly, the both is quite close, 0.2 Tesla about this material. But all this work still ongoing. That means we should optimize again our powder, find some parameters, and so on. Okay, let me just come to the conclusion. Say the fast heating SPS allow us to prepare the dense bulk magnesium diboride cryomagnet, where he was able to trap roughly 4 Tesla at 20K on these materials. Then regarding now the permanent magnet, the powder can be sintered. It's why we demonstrate in the first part of our ongoing project. And we observe also some low variation of coercive HC after SPS sintering. In the recycling powder permanent magnet, we was able to obtain this 0.2 Tesla. But now the next step for us is to optimize the magnetic properties by investigate again the sintering parameters, pressure, temperature, the powder to analyze. You also take care about the powder oxygenation and so on, like I point out. Thank you very much for your attention.